So in this MP4, we're going to run an Anova. We have some data here from the Pennsylvania Department of Health. It's nursing home beds, occupancy, resident cases of COVID-19, resident deaths from COVID-19, and staff cases from COVID-19. The variable abbreviations in our data are set forth here. We use a C for cases, D for deaths, and an S for staff cases. The data are in Blackboard as Pennsylvania Long-Term Care COVID, saved. And we've got these counties coded as Allegheny, Dauphin, Philadelphia, and Montgomery. Here's a picture of the data loaded in Spss. So you can see the name of the facility, the city, and the county code, which is our county code, number of beds, census, and here's resident cases, resident deaths, staff cases, and here are our normalized cases, deaths, and staff. Our hypothesis is that there's no difference in COVID-19 cases per occupied bed in Allegheny, Dauphin, Philadelphia, and Montgomery counties. The alternative hypothesis is that there are differences. Just to review, and it's in the lecture slides, the types of data that we need for Anova are an independent random sample. The independent variable is nominal. That means we need 3 or more groups. There's only one independent variable. Our dependent variable must be continuous. Each group distribution needs to be normal, and we need homogeneity of variance from the 4 groups. And also we need sufficient sample size, which is going to be basically at least 10 observations per group. So with Anova, we calculate the variance of each group, and then we calculate the variance of the total group. And if the total variation is the same as the average of the variances of the individual group, then the means of the groups won't be different. So we're looking for some differences among means. If the group variations add to the total variation, there's no between group variation. Post hoc, if we find that some of the means are different, we'll need to do a post hoc test to tell which are different. The type of test depends on the type of data and comparisons. So here, this is sort of conceptually what's going on. We find a sum of squares between groups, just like we did before with sum of squares for means. And we find a sum of squares within groups. We calculate our degrees of freedom between groups, which is the number of groups minus 1, and the degrees of freedom within groups, which is the total number of observations less the number of groups. So that gives us the mean square between and the mean square within. We divide this into this. And the F ratio is the mean square between divided by the mean square within. The total sum of squares back here is SST. So that's what we're doing conceptually. It's pretty simple in SPSS to get it in. Our commands are analyze, compare means, one-way Anova, and we put in a measure for dependent and years for grouping. So let's go over here to our data. So before we do this, we're going to be doing checking for normality. So we do graphs, legacy dialogues, histogram, and we put in our variable name. It'll be over here for you to begin with, and you just put it in here. So cases per occupied bed is our variable, and code is our rows for our histograms, and we'll click OK. And so here are the histograms for our 4 groups. As you can see, they're not particularly normal, and we've probably don't have enough real observations here for Dauphin, but let's try it anyhow. So now we're going to do the Anova itself. Analyze, compare means, one-way Anova. And again, we want to put cases per occupied bed as our dependent. We're going to put code for our factor. And we're going to click this post hoc box so that we can do post hoc comparisons. And you're going to want to check Tukey. Continue. Okay. And here's our output. Up top, it gives us the sum of squares between groups and the degrees of freedom between groups and the mean square between groups. And the same thing for within. It calculates our F statistic, which we can see is pretty high. And we don't even bother with an F critical value. It gives us a significance here, or a p-value of 0.000. So this is significant. Now we go down to the multiple comparisons. And here is region 1 versus region 2, not significant. Region 1 versus region 3, that is significant. Notice the lower bound and the upper bound here in the first one, zero's in it, so that's, again, not significant. 0 is not in these bounds here. Also, in 1 versus 4, we've got significance, and the value, right, the amount of the difference here is very large, so you've got a good effect size. If we look at Dauphin County, there are no significant pairs. Philadelphia County, the only significant pair is Allegheny, and Montgomery County, the only significant pair is Allegheny again. So basically, we see in the Anova that it was significant. We can reject our null hypothesis and accept our alternative hypothesis. And conclude that there is a significant difference between Allegheny and Philadelphia counties in terms of coronavirus cases per occupied bed, and also that there is a significant difference between Allegheny County and Montgomery County. And in each case, the difference is substantially less.